In today's lecture, we're going to be very ambitious. I have a number of goals for you. Our overall plan is to learn how to leap into extra dimensions. Most, I believe, of the fascination with string theory that we see in the public is partly derived from the fact that physicists are talking about extra dimensions. We're going to need to get comfortable with these extra dimensions because string theory allows for them. How are physicists able to think about extra dimensions? By taking the mathematics from the world around us and applying it in a hypothetical world of other dimensions. If you know the famous little book, Flatland by Edwin Abbott, its goal was to help you to visualize extra dimensions using pictures and words. My goal is very different. I want you to gain insight about how physicists use mathematics to think about, to study higher dimensions. We're going to talk about string theory in detail, and next lecture, we'll actually start picking up some of those strings. And most physicists believe these involve extra dimensions. Not necessarily this physicist, but we'll get to that later too. We need to spend a little more time with algebra and geometry in order to prepare ourselves. The Pythagorean theorem is the simplest piece of mathematics that will give us the biggest bang for the buck in increasing our understanding as we move to more complex details of string theory. It's the piece of mathematics that will open the door, or at least can open the door, to understanding higher dimensions. I can now ask, what if our world had one or more extra dimensions? And as a string theorist, that is to me a central question. I'll be using the Pythagorean theorem to show you how physicists don't necessarily visualize extra dimensions, but instead calculate the properties of objects in those higher dimensions. Why is this important? Because in this lecture, we will see that this relatively simple but very key mathematical idea was used by Minkowski, one of the mathematicians we talked about earlier, to simplify Einstein's ideas, including his famous equation E equals mc squared. In fact, this equation actually comes from Minkowski's elaboration of the Pythagorean theorem. In later lectures, we'll encounter Minkowski's elaboration of what I now in this lecture will call the Einstein hypotenuse, and it will be encountered over and over again, discussing ideas like tachyons and symmetries. You could well ask, what are those? I'm just going to have to say we'll find out later. Now, Pythagoras of Samos was not actually the person who discovered that the sum of the squares of the lengths of the sides of the right triangle is equal to the square of the length of the hypotenuse. Over 1,000 years before his birth, the Pythagorean theorem was known to the Babylonians. However, he was an astronomer, the first person to propose that the earth was a sphere at the center of the universe, a mathematician, and a philosopher. To see why the Pythagorean theorem is true, a simple diagram will help. So here we have one. Now, here you can see we have a couple of lines, and there's a green line, and we're gonna do something with this, and we're gonna actually figure out something about its position. Notice that under the green line, we're going to have a bunch of boxes appearing. So let me first of all set this in motion. So there are green and blue lines, and we can see that we have a set of boxes there. Now, you can see that the length of the green line and the length of the blue line are the same. The green line is the base of the square, the blue line is the top of the square. And because they're both the same, it means the two areas are the same. In the bottom of this transparency, you have a little equation. It says the area of the green is equal to the area of the blue. Now let's continue all of a sudden to go this point. What you see now is that we have three boxes, but what we did was to take the green line and simply lift it up. Now that creates the green line. Well, it's still there, and since we lifted it, its length didn't change, but we created a new line by lifting its edge, and we've colored the square associated with that line brown. And we still have our blue line. When we lifted the green box up, if you look very carefully, and let me run this backwards a little bit, you'll notice that as the green line goes up, the blue line had to shrink because it had to stay directly under it. And therefore, the blue square had to shrink. Now, you'll notice our equation has changed because now we see that the area of the green is equal to the area of the blue plus the area of the brown. And the remarkable thing about this result is that no matter how I orient the green line, the area of the green is always equal to the area of the blue plus the area of the brown. Now, that very simple picture is what we mean by the Pythagorean theorem. Now, there's one other thing that we can do that perhaps you've never seen before. Now, let's talk about area for the moment because area is an interesting concept. Suppose that you wanted to buy some carpet to lay down on your living room floor. You would go to a store, and you can't just walk in and say, I want some carpet. You have to be able to tell the salesperson exactly the size of your room. In order to do this, you have to talk about two sets of numbers. So what are those numbers? Well, if we walk into your room, let's call this direction here length, and we'll call the other direction breadth. So I take a measuring stick or a ruler, I measure the distance from myself to the wall in this direction, that gives me one number. Then I measure from one corner of the room to the other, that gives me another. The area I get by multiplying these two things. And this is a well-known process that many of you probably have done if you try to go out and buy carpets. Now, the interesting thing about this process is if it's a square, the length on one side will be exactly the length of the other. And that's what we see here with our boxes. We weren't talking about any old shapes of rooms. We were talking about squares. So we have seen now that some areas in this picture are related. What if we actually continue this process? In this picture, you see the green line. And what I can do is to take the green line and do one other thing to it. Imagine that it was laying flat on a plane. I could lift it up. In my computer animation, it looks like this. You'll notice something interesting happened just then. I now have 1, 2, 3, 4 squares. A green square, a blue square, a brown square, and a purple square. Where did that purple square come from? Well, when I take the green line and lift it up, it's a certain height off the ground. So there's one more square that I can construct. And now, there's something really remarkable here because the area of the green is equal to the area of the blue plus the area of the brown plus the area of the purple. Now, that's probably something that you've never seen before. That is also an equation, and in order to get some sense of this equation, it's useful for us to go back and look at the simpler equation where we didn't lift it up. And so let me run my picture backwards so that we see only 3 squares, and there they are. And now what I want to talk about is how do we describe this in terms of some mathematics? Well, remember I told you we couldn't avoid algebra, so here we are, we're right in the thick of it. You see, there's an equation on the screen now, and I've written it in words. It says the area of the hypotenuse is equal to the area of leg 1 plus the area of leg 2. And what does that actually mean? Well, in our pictures, the area of the hypotenuse was the green square. And so the green square's area is equal to the blue square's area. That's what we're calling the area of leg 1, plus the brown square area. That's what we're calling leg 2. So this is the Pythagorean theorem, as perhaps you remember from high school. It's exactly what would happen, in fact, if we put a ladder up against a wall. So here's a house. And next to the house, you can actually see a ladder. Let's walk over there. Here's a ladder. We still see it laying flat on the ground. And now we're going to use this ladder to construct 2 squares. One square will be above the ladder, and the second square will be below the ladder, much like our diagram. And there you see it. Now, Because the ladder is the base of one square and the top of the other, those two areas are the same. I can lift the ladder up, just like we did in our diagram, and when we do so, we see that the relative size of the blue and the brown squares change. But the sum of those two areas is always equal to the green area. In fact, we can lay the ladder perfectly vertically along the house, in which case we get this representation, and then only the area of the brown is equal to the area of the green. But there's one more thing that we could do. Let's pull our ladder back away from the wall. Now it's vertical. Now, don't do this at home, but if I have a ladder stacked up against the wall of a house, I can always push one edge of it, the one closest to me, away from the vertical. If someone is on the ladder, that's very dangerous, but let's imagine doing that. In order to push it over, I have one more distance. It's the distance from the ladder, from the base of the ladder to the wall. There's a distance from the ground up to the height of the ladder where it touches the wall, and then there's the distance I have pushed the ladder over. And that gives us this third purple diagram, purple square, as we see in our diagram. That's what we were talking about in our previous picture. Now, we also talked about algebra, so let's go back to algebra, because algebra is a very interesting subject and actually very important. In the late 90s, there was actually a study done by the Department of Commerce in which the question was asked, if a student doesn't take algebra in 9th grade, what percentage of jobs will that student not be qualified for when they enter the workforce? The answer back then was 45%. In other words, in a knowledge-based economy, an environment with information age technology, this kind of understanding of algebra becomes very important. Now, algebra was in fact an export from Iraq around 830 AD. A scholar from whose name we derive the word algorithm, which is a shortening of his last name, which was Khwarizm. We use this to describe a process by which rules of mathematics are manipulated. In fact, his work, which was later transported to Europe, is where we get the word algebra. Algebra was the original pronunciation. So when we write an expression for our ladders, we can use algebra or algebra. And that's what we did earlier. H square, that's the area of the green. L1 square, it's the area of the blue. L2 square is the area of the brown. In tilting our ladders, we need a different mathematical formula, a different piece of algebra. And I've written that on the bottom of our image. Here we see H square is equal L1 square, L2 square, and L3 square. L1 square is the area of the blue, L2 square the area of the brown, and L3 square the area of the purple. So you might say, well, gee, in going from 1 to 2 dimensions, all we did is add one more area and said the green area is always equal blue, brown, and purple. So how do you go to 4, 5, or 6 dimensions? Well, there's kind of an obvious thing to do. Instead of adding just one additional square, you could add 3, 4, 5, 6, or 7. And in this way, you would have a Pythagorean theorem that works like our picture in our world, but yet would apply to a world with more dimensions. Now, this way of understanding how to do mathematics, that is, take a formula that applies to a real object in our world, write an algebraic expression for it, change that algebraic expression and ask what are its new mathematical properties, that's the kind of thing that we physicists do when we talk about extra dimensions. Now, notice that the Pythagorean theorem actually came to us by looking at areas. And in fact, my suspicion is that that's the way that the ancients actually discovered the Pythagorean theorem, by simply noticing areas. So what can we take away from this experience? Well, the way to study extra dimensions is by first studying mathematics in our dimensions, in 3 dimensions. Try to uncover patterns or rules, things that, for example, are the same no matter how you orient the ladder, and then take those rules and slightly change them. So there's nothing sacred with having just 3 squares. We could have more. And that's what we saw when we want to talk about physics in higher dimensions. The secret that we use for getting to higher dimensions is that we do not, as theoretical physicists, visualize higher dimensions per se. We write down mathematical equations and then use those equations and change them. Now, so does our world have more than the 3 directions? Well, we don't know. I can tell you some things about our world that are true. In our world, there are 3 independent directions in which we can move. We can move front to back, we can move left to right, or we can move up and down. And if you stop and think about that number 3, that exactly works with the last form of the Pythagorean theorem that I described. Now suppose that there would be 4 directions in our world. Then in fact, there would have to be 4 areas. We would write, there would be 1 front to back, 1 left to right, 1 up and down, and then 1 more, which we've never seen. But if the 4-dimensional world that we're thinking about is to act like our world, then the Pythagorean theorem in that 4-dimensional world would have to act like the one that we know. And so it would be a statement about areas in exactly the way that we've described. So this exercise of attacking the Pythagorean theorem and thinking about it in terms of pictures and areas is what we physicists do when we try to describe higher dimensions. We look for a piece of mathematics in our world. We study its properties, and the properties that we've seen are something is the same. Green is always equal to blue, brown, and purple, no matter how you orient the object. And by the way, this whole issue of change is one that we're going to see many, many times. In fact, we have also touched upon something that is much more interesting, and we are prepared for 4 dimensions. So let me tell you a story. Suppose that I went to a bar and I went and ordered a drink, and bartenders are supposed to be very good people to talk to. So let me begin a conversation with my imaginary bartender. I might have a concerned look on my face, and if I said something like, Joe, I've got this concern about the 16th dimension, the bartender would have a really difficult time wondering what I'm talking about. Now, if I tell him that it's mathematics, then perhaps he no longer says, gee, I might not know how to do that stuff, but it's not magic. So when you hear people in string theory talk about extra dimensions, what you should understand is that we physicists are worried about mathematical equations that have some attributes that are exactly like the equations that we've seen in our 3-dimensional world, but where we allow for the possibility that there might be extra directions. So instead of the directions that we know about, perhaps we add 1 more, or perhaps 2 more, or perhaps 3 or 4. Now, the remarkable thing is that some of the mathematics of our world is such that when you change the number of directions, the equations look pretty much the same. This is, in fact, so important that we physicists actually call this invariance. That is, you change something, but there's a property that's left unchanged by that. Now, we're going to be using invariance in many, many ways in the future. You notice with our ladder, I talked about trading the area of the blue for the area of the brown. But when we do those changes, the area of the green was the same. We're going to be changing many things in this course, not just areas. We're going to talk about other kinds of changes. And when physicists talk about changes that leave something the same, that's what we mean by symmetry. Symmetry is going to be one of the most important things that we will develop in this course. So, we can talk about, for example, in our world, a sphere. A ball. A sphere is you can think of that as a ball. And if you remember some of your high school mathematics, there's an equation that tells you if you measure the distance from the center of the sphere out to its side, that distance is called its radius. If you take that number, you multiply it times itself 3 times, then you further multiply it by the number pi, and then multiply that again by 4 and divide by 3. Gee, sounds like a mess, but let's say you do that. The result that you get out of this is the volume of the sphere. Suppose we want to calculate the volume of a box. Well, to calculate the volume of a box, well, what's a box? Well, it's got to have a front-back distance, a left-right distance, and an up-down distance, so it has 3 numbers. Suppose you want to calculate the volume of the box. It's the product of the front-back distance, the left-right distance, and the up-down distance. So, in our world, I know how to calculate the volume of balls. I know how to calculate the volume of boxes. Suppose our world had 4 dimensions. How would I calculate, for example, the volume of a box? Well, remember, what was interesting in our world was front-back, left-right, up-down. In a bigger universe, let's imagine it had 1 dimension more, there would be front-back, left-right, up-down, and this other number. Now, we've never seen this other number in our world, but remember, we're now in the world of mathematics. And mathematics, as long as you're consistent with your manipulations, doesn't care. So how would I calculate the volume of a box in 4 dimensions? Well, in 3 dimensions, we know how to answer the story. You multiply 3 numbers. In 4 dimensions, we have 4 numbers. So what do you do to find the volume? The answer is you multiply all 4 numbers. So, higher dimensions is not magical. It's the extension of ideas that we see describing things in the world around us. Now, the interesting thing about this process is that you might think of this as something new, this idea of higher dimensions. But in fact, the development of mathematics has been such that mathematicians and physicists have actually known how to calculate the volumes of objects in mathematical universes of more dimensions since the time of Leibniz and Newton. Remember, Leibniz and Newton were the inventors of calculus. So as soon as mathematics acquired those tools, mathematicians certainly knew how to, for example, calculate the volume of a box in 4 or 5 or 6 or any number of dimensions that you care to think about. They knew immediately, even prior to calculus, how to extend the Pythagorean theorem. And so when we talk in science about extra dimensions, we're talking about the extensions of equations. Well, mathematics is completely straightforward, but we don't necessarily, when talking about mathematics, describe our universe. Please note that in my discussion, algebra was absolutely essential, because that's how we use to describe the extension of the Pythagorean theorem. We use algebra to describe the areas of the squares, no matter how we orient them. We actually have to use calculus to describe the area of spheres. So let me, although it's possible for me to give a lecture like this or a series where I'm discussing aspects of string theory, I'd like to keep you focused on a kind of an allegory. You have to remember that whenever I'm talking about string theory, I'm telling you really an allegory. I'm telling you something that's like a poem. I'm speaking about something that's like an analogy. I'm not telling you the complete truth. So, for example, I haven't bored you with an endless recitation of mathematics, even though it may have seemed that way. Mostly I have talked about pictures. Many times when people talk to me about string theory who are not scientists, who are not mathematicians, they often ask the question, is there something that you can do without the mathematics? The answer, truthfully, turns out to be no. You see, the mathematics is the only firm guide that we humans have to think about worlds with extra dimensions. We've never seen any extra dimensions. We cannot conduct experiments there, or else we would have already done so. And so it turns out that the mathematics is the only precise way in which we have tools for exploring these extra dimensions. Are they really there? That's another question people often ask. And the answer is, we don't know. Later we're going to study more about the structure of string theory, but for now let me tell you that string theory, and remember it's a set of equations, allow for extra dimensions. In the next lecture we're going to see why this is true. And it's going to come back to some very interesting questions about pasta. Oh, wait a minute, what do I mean by pasta? Well, in a very early lecture, we talked about the fact that when you study string theory, you're talking about the mathematics of objects that we can picture as filaments. So, in some sense, strings do in fact look like pasta. The question that's going to be our challenge is the following. You see, all of the physics, since Isaac Newton, remember, he is the creator of modern physics, all of that physics is based on the notion that if you want to understand our universe, you should first study little balls. It has not a place for you to begin the study with little strands, or what I just referred to as little pieces of pasta. Now, for several hundred years, from the time of Newton to the present, this notion that little balls is good enough has gotten us a tremendous amount of progress in understanding science. It also has evolved. It has been shown to be consistent with the world of special relativity, where time can be traded back and forth. It is also consistent with the world of the quantum denizens. Now, if you believe in string theory, and that mathematics suggests extra dimensions and these filaments, then in order for that mathematics to describe our reality, we have to know whether it is consistent with special relativity and the quantum world. Can we put, in some sense, filaments into these quantum worlds, and to have the filaments to be as small or smaller than the denizens we see in the quantum world? This is a non-trivial question to ask. It was first asked in the 1960s, and the answer that came back from the study of these equations was absolutely stunning. It turns out that when we take these two pieces of science from our world, relativity, quantum theory, package them together with filaments, this combination of three things is going to drive us into extra dimensions, into believing in extra dimensions, or at least it will seem that way at first.